This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So in the last lecture, we derived the heat conduction equation. So there, this equation allowing us to do basically everything in terms of the conduction problem. And the primary goal, as we mentioned, for the conduction problem is to find out the temperature distribution within this conducting medium. So this conduction equation we derived is for the most general case. And if I can repeat it there. So this one allowing us to determine the temperature distribution within a three-dimensional medium if you're using Cartesian coordinates x, y, z, and then also as a function of time. Right. So this is the most general case, and in the problem we are seeing in this subject. We mainly only dealing with one-dimensional conduction, right? Even though later on a certain problem we discussed, for example, for the extended surface conduction, the heat transfer can happen in multiple directions, but the conduction we consider there is still one-dimensional. All right. So, in terms of simplification, what you're often dealing with, or in this subject, you're always dealing with is three-dimensional to one-dimensional. All right. Basically, you can get rid of two differential terms straight away, and then we consider the thermal conductivity is a constant. Then we can consider that the heat generation term is not there. Or we can consider that the problem is a steady process, which means you don't need to consider the temperature variation as a function of the time. Right? So this condition is always there for the problem you're seeing in this subject. These three, sometimes they all there, sometimes two of them, or sometimes one of them are there. Okay, you need to know how to dealing with the differential equation or simplified version of this general equation for different problems. So what we are going to do today is basically to study some simple case. That's one-dimensional conduction. And we will discuss two problems. One is really straightforward, although there is many application just using that type of problem. And the other one is also simple. It's still one-dimensional steady problem, but it's a little bit different. It's based on a different coordinate system. So conceptually it's still simple, but in terms of the process, can be a bit different. All right. So the first thing we discuss is called plane wall conduction. This is the simplest case. Basically, we simplify this general equation to the maximum extent. So, if you consider a conduction through a wall, and the wall has certain thickness, has certain height. Right, so if we using the air to represent its thickness, has certain height and also has certain width in that direction. In order for the problem to be approximated as a one-dimensional conduction, you need to satisfy basically two conditions. So you have the thickness or the air there should be much smaller than the height and the width there. So it's a relatively thin wall. So that's the first condition. The second condition is you have the isothermal wall surface. So for example, the temperature there is T1, temperature there is T2. And for the entire surface, which is formed by the W and H, that's one temperature. One is equals to x 0 to that direction, right? So when x equals to 0, that side of the wall has one temperature, and x equals to air, that side of the wall has one temperature. But this temperature certainly different, so that the heat transfer can happen. So this basically the two conditions, and many applications actually satisfy this, these two conditions. So with that, we can just simplify our equation. And if we further assume for 1D to be valid, right? And with that, we further simplify, consider that K equals to constant, Q equals to 0, and it's a steady process. So if you're looking at the equation we're having here, this term still there, these are gone, these are gone, these are gone, and this is gone, right? So we only got one term left, so we can move the K outside the differential because it's a constant now. So partial T partial x T square x square equals to 0. So essentially the K then can be get rid of, and then we have the dt dx square equals to 0, right? Because there is no partial differential required. So this is the equation we got for this plane wall conduction problem. This is the simplest, as simple as you can have. And with this equation, if we want to solve the problem in terms of how to find the temperature distribution in the conducting medium, what we need to do is, so this is a differential equation. We need to integrate it for the domain or for the object we're dealing with. Basically, we need to do integration, right? So that should be all straightforward. So we integrate once, dt dx equals to c1, and then t equals to c1x plus c2. So that's no problem at all for this simple second order differential equation. And then to solve these two unknowns, we need two boundary conditions. So this constant there needs to be solved, which means you need to find out two boundary conditions for this problem. So two boundary conditions. So one is when x equals to 0, temperature equals to T1. This is what I referred there. And x equals to L, T equals to T2. Then bring these two there. You can find the temperature distribution, T1 minus T2, T1 divided by L and times x. So this is a temperature distribution. So there are no point to going through this mathematical process. So when you bring in these two conditions, you will find the C1, the C2, then you will get that. Right. So this is a temperature distribution within this plane wall, which have two temperatures on each side. And as we said, this is a very simple problem, but it's we follow the procedure that when we dealing with more complicated problems, there's the same procedure. So the procedure is more important than the equation because the results we are already known more or less, right? So we find out the temperature distribution. The next step is to find out the heat transfer rate. The heat transfer rate, how do we obtain the heat transfer rate? If you know the temperature distribution, how do you get the heat transfer rate? That's very loud. Rate equation. Yep. Fourier's law, essentially. So you have you know the temperature, how temperature distributed in a medium, and the rate equation for the conduction, that's Fourier's law, which containing the temperature distribution term there. So if you recall, that one is K A, have minus there, and dt dx. So you bring in the dt term, dt equation you already obtained, then you will have the K A T1 T2 divided by L. All right, so this equation actually we mentioned before when we first introduced the rate equation for the conduction. But this is coming from the analysis of this general case, right? From the general case, how we obtain this equation is from apply the first principle to a differential volume, and then energy balance from there, and bring in the rate equation. We got this equation, we got this general equation. Then when we study a specific problem, we apply the simplification that we can apply to obtain this equation, right? And this equation, when you integrate over the domain of your practical problem, then you find a temperature distribution of there, and then you can calculate the heat transfer rate. So it's going from a differential element to a overall microscopic element, microscopic object. So that's the process. You're starting from, you analyze a local problem, and then you can solve a global problem. So there, if we draw the temperature distribution, that should be straightforward. So if from 0 to L, and the T1 and the T2, that give us a straight line. So that should be straightforward. One application of this plane wall is like this. So if you ever see a new house or new building being built, nowadays they consider that the building needs to be energy efficient. So what typically it does is you have a double wall for the house. So basically you have wood or other low thermal conductivity material, and you have a layer of air sandwiched in between. So that's for the wall of the building. And also in terms of glass or windows, that's also a similar idea. So this is so-called double glazed window. And you have basically 2 layers of glass. And you have 1 layer of air sandwiched in the middle. So the idea there is to, you have a layer of air which has a lower thermal conductivity, very low thermal conductivity. So in summer, if the inside is cool, it can prevent the outside heat to get in. So basically, it's a barrier, it's a thermal barrier or thermal insulator. And then in winter, if the inside is warm, it can prevent the heat got lost to the outside. So that's a problem that we can use as an example of the plane wall case. So let's say the application. So if we can draw the schematics there. So let's say this is one wall or one side of the wall. And then you have the air, which is sandwiched in the middle. So one side of the wall has certain thickness, and the air layer has certain thickness, and the other side of the wall also has the thickness. Right? So this air is not moving, which means the heat transfer through it would be conduction. But you have the air inside and outside, or also have the air inside. Right? So those air are not necessarily static. That can move. So you will have the conduction happens. Let's say this is outside. You will have the infinity or the ambient temperature of outside, and you have the heat transfer coefficient as outside. And then similarly, if you have the air inside, it can have some natural convection happening, and HI inside. So this is a typical multi-mode heat transfer involving convection and conduction. And what we can do, we can use the thermal resistance concept that we learned previously to study this. At the very outside, we have thermal resistance. Let's say this is a convection out. And then see the first wall, which is a conduction of the wall outside. And then we have the conduction through the air. Then the other one is wall inside, and then the convection inside. So there's 5 elements in this system, and they are being put together in series. So if I have the outside temperature is hotter, then the heat will be transferring in that direction. So when the system is put together in series, we can determine its total resistance by adding all the elements together, right? So the R total is equals to the sum of the each one, and we can write it based on the thermal resistance equation we discussed previously. So for convection, we have the HO times the area, and this area we know that should be the area which is perpendicular to the paper we have here, right? Normal to the heat transfer, heat conduction direction. So that's the first one. Then L1 K wall times area, so that's corresponding to this one. L2 K air A, and L3 K wall A, and 1 HI area. The thermal resistance is something to help us in terms of calculating the heat transfer, right? So the thermal resistance would equals to, we can use it in different ways. The heat transfer, as we said, can be written in terms of the total resistance over the total driving force over the resistance. So because this is a series problem, the different elements being connected in series, the Q is the same passing through this process. So depending on what temperature you use, and you should I should say you should use the temperature difference corresponding to the resistance for that part of temperature difference. So if I apply the total temperature difference, then I need to apply the total resistance. That's the point. So if I have the T infinity O minus T infinity I, so apply the overall temperature difference, then I need to apply the total resistance. So by the same concept, if I know the thermal resistance for one segment of the process, then based on knowledge of the total heat transfer rate, I should be able to determine the temperature difference across that component, across that segment. For example, if I have this one as T wall O outside, right? So this one is a T wall O inside. I can have the temperature difference there figured out based on the resistance across this length. So that should be L1 K wall area. So because the things are all connected in series, just like electric circuit problem, you know the current and you know the resistance, then you know the voltage drop, right? So that's the same concept. And if you draw the temperature distribution there, so if that's the temperature and that's the length, right? So if I have this L1, L2, and L3. So if I starting from the outside, which is T infinity outside, we have convection. So convection have the temperature distribution actually looking like this, which we are going to discuss later on. It's not linear, for sure. Then you reach the outside wall of the outside surface of the outside wall. Then you will have a temperature drop there, and then going through the air layer, have a further temperature drop, and then going through the inner wall, and then going through the convection inside. So if you have a like thermometer can measure temperature, then you will at each position, then you will have a temperature profile look like this, and each segment corresponding to a certain temperature drop. And based on that temperature drop, you can tell the thermal resistance for that segment. So, for example, here I have certain temperature drop across L1, and I have another temperature drop across L2. And the temperature drop corresponding or proportional to their thermal resistance. That's the things I'm saying now. So the temperature drop is proportional to the thermal resistance. You see a larger temperature drop, which is saying it has a larger thermal resistance. A smaller temperature drop, which is saying that material is efficient or effective in terms of conducting heat. When heat passing through it, there is a little loss or little temperature drop. So if you have a poor conductor, then you will have a larger temperature drop, which means it has a larger resistance in terms of for the heat passing through. All right, so that's something you want to be aware of, a larger temperature drop, which means larger resistance. All right, so this is a problem. It's very straightforward, and both in terms of the theory and in terms of application, and in practical conditions, actually, there's quite a bit of problem can just be described by this simple case. The next one is also pretty common, and it's a one-dimensional conduction as well. So this one is a one-dimensional cylindrical conduction. So here we consider that we have a pipe. For example, it can be a like electric wire or can be a steam pipe that you have certain heat is generated inside. All right. So if I have the pipe has certain thickness and I have inner surface at one temperature and outer surface at another temperature. So let's say this is R1 versus R2, and then you have a length. So we're using length there. So in order for this type of, you have something hot inside. All right, it can be hot or cold, but in most cases, it's hot inside. For this type of problem, if you want to apply a one-dimensional heat conduction, so there's also two conditions that you need to satisfy. One is the radius R1 and R2 must be great smaller than the length. So it's a relatively small diameter pipe, but it's very long, right? And the other one is the temperature of the inner surface needs to be uniform, which is also isothermal inner surface and isothermal outer surface, and they are at a different temperature. So R1, should say T1 at R1 and T2 at R2. And these two are certainly not equal. Then you can treat this type of problem as a problem we are going to discuss. One-dimensional problem, and going from inside to the outside. All right. We're dealing with a different coordinate here. It's not x, y, z, but we can apply the similar concept or similar approach we learned before. So, for example, if I draw a larger cross section, so this R1 and R2. We have heat which is coming from the inside and try to go through this thickness, right? So I should say in this case we also have the K equals to constant and the Q dot equals to 0, and we deal with a steady problem. So the same setup compared to the plane wall, except we're dealing with a different geometry here. So in this case, we choose a radius there as our control surface. So anything between R1 and R2, we choose one as a control surface, then apply the first principle to that control surface. So on that control surface, let's say we choose R between R1 and R2, and the energy balance there. So in this case, if we have the E in plus E gen equals to E out and transient, we know that this one is 0, this one is 0. Only in equals to out, right? So if we do that, we can write the Q heat transfer as the radius R equals to, if this one has any thickness we can apply, we can just say R plus dr across that. Maybe to be more accurate, I should draw, it's not just a surface, but it's a slice of the radius. So you have a certain radius coming in as the QR, and a certain heat coming as a QR, and a certain heat leaving it as the QR plus dr. Right? So this one you can do a simple rearrangement and get the differential equation. So like we did before, we can move this term to the other side, R plus dr minus QR, and if we divide it by a dr, then let's do equals to 0. and apply the relation we learned yesterday, which is fx plus dx minus fx divided by the dx, and when the dx is approaching 0, you will have the dfx dx. Right, so that's the definition of the differential. If we apply to there, we would directly get the q dr that equals to 0. So basically, that's a simple statement is saying that the heat is transferred at a steady rate across the radius. There's no storage happens there. So then we bring in the rate equation. So this is the energy balance equation that we, by analyzing a differential control volume or control surface in either way, then we get this one. We need to bring in the rate equation. So which means we bring in the Fourier's law minus Ka dt dr equals to 0. So I should say bring in rate equation. All right, we said K is a constant, so the K can be gone. Right? And then we have the area and the temperature gradient. This area is what area? How do we describe this area here? The area of diameter times the length. Yeah. So that's area which is the surface area corresponding to this one, right? From there to there and to there. That's the area where the normal to the heat conduction direction, right? So this one should be 2 pi r. That's a parameter, and times the length. Oh, sorry, it's not parameter, it's diameter. Diameter times the length. So, no, it's a parameter. Yeah. So this one times the length, that's the surface area where the heat is being conducted. So this one containing a variable there, which means we cannot get rid of the A just like we do the plane wall case, right? For the plane wall case, the area is not changing along the variable. But here, this area is a function of the variable, which means we need to at least keep this R term there. So these two can go. Then we end up with d dr r dt dr that equals to 0. All right, so this again is a second order differential equation. What we need to do is just integrate it and then bring in the boundary condition that is available for the problem. So just the 2 rounds of integration, then r dt dr equals to C1. And the second round is dt dr C1r, which means t equals to C1 log r plus C2. All right. So again, 2 constants requiring 2 boundary conditions. Again, what I'm showing here is a procedure. All right. So the problem may not be that complicated, but the procedure what I'm showing is you use for more complicated problems. So there you have the R1, T equals to T1, and R equals to R2, T equals to T2. So bring these two to solve those two constants, then you will find the temperature is T1 minus log R minus log R1 ln R2 minus ln R1, and then T1 minus T2. Right, so this is a temperature distribution inside this cylindrical tube. So if you plot the temperature there, so if you have R1 and R2, and at R1 you have a higher temperature T1, and R2 you have a lower temperature T2, right? If you plot this relation with temperature versus R, it's not a straight line for this case. You would have rather you have a curve to connecting these two points. So that's just because you're dealing with a long term instead of a linear term. So that's a temperature distribution look like for this cylindrical case. So if I asking you what's the temperature, what's the heat transfer rate across this cylinder, with the temperature distribution solved, then we just bring in the Fourier's law, right? So minus K A dt dr. You bring in the temperature distribution you already solved to this equation. So then if I have the K, again the area is the same area we just mentioned for the conduction to happen. So that's 2 pi r L. So it's depending on where is your radius. Actually, this can be a that certainly is not necessarily a fixed value. Then you bring in the temperature equation you already solved. Then you will have the T1, T2 log R2 log R1 and 1 over R. But you will realize that ZR and ZR got cancelled. So you end up with T1 minus T2. Sorry, I should get rid of the minus sign when I'm doing this. Then I will have the log R2 log R1 and 2 pi K L. So you can, by calculating the heat transfer rate and bringing the area, bringing the temperature gradient coming from your temperature distribution, you end up with a Q, which actually is a constant for the given problem. So the every term here is a constant, which is certainly consistent with the things we derived before. At one stage of the derivation, we find that dq over dr equals to 0, which means the q must be a constant with respect to the radius, right? So this one is a constant. So that should be the case. And then we recognize the thermal resistance for this case should equals to the denominator term I wrote there. That should be your thermal resistance term, which is temperature difference divided by the thermal resistance equals to the heat transfer rate. So that's the term that we obtained from this analysis. So that's the case for the cylindrical conduction, one-dimensional. And we are going to discuss application of this problem as well. So in this case, for example, if you have a copper wire which you use to conduct electricity, and a copper wire, when it's when the current flowing through it, it will generate heat, right? And often you want to put some insulation outside. So one purpose certainly is to prevent electric shock, and the other purpose is if the surface is being too warm, you want to conduct certain heat away. So that is a case where we can apply what we learned here. So similar condition. If you have a steam pipe flowing and you want to prevent the heat lost during its flow path, then you need to apply certain insulation. That's similar to the problem we are talking about here. So for this type of problem, if we're looking at the thickness of this, either the insulation layer or the thermal insulation layer or the electrical insulation layer, we can apply the problem we are learning here. So for example, if this is R1, so where the source of the heat generation, and this is R2. If we derived how the temperature should distribute within this layer from R1 to R2. That's what we learned before. And if we apply the energy balance for the outer surface, if we consider the heat transfer or energy balance on the outer surface, then we will find that you have the heat conduction coming into that surface from the inner layer or the inner of the tube. And then because this pipe or this wire is often exposed to air, then you have the convection happening to the outside. So there you would have the conduction happen as a inflow to that surface, and you have the convection happen, which is taking the heat away. Right? So this again is a multi-mode heat transfer problem, and these two processes happening in series. Right? We can use the simple thermal resistance concept to describe that. Then we have the conduction and the convection. Only two for this case. And the total equals to the sum of it. The conduction is, we can borrow the equation we derived just now. Right? So that's log R2, ln R2 minus ln R1 to pi KL. And the convection is the heat transfer coefficient times the area. That area is the outer surface area corresponding to R2. So that should be 2 pi R2 and times the length there. All right, so if you're looking at the the two terms, both terms containing R2. R2, if you consider R2 is we consider R2 is the outer surface, which essentially is the radius from the inner part, the radius difference from the inner part to the outer part. So the R2, if the R1 is for example, is a wire, it has a fixed diameter, or it's a pipe, steam pipe, is a fixed diameter, then the difference between R1 and R2 will determine how much is the thickness, what's the thickness of the insulation layer you want to apply, right? So R2, if R1 is fixed, R2 will represent how thick is your insulation layer, right? If you're looking at the equation there, if you're increasing R2, which means you're increasing your insulation layer thickness, this term, which is R conduct, will goes up, right? Because that's in the numerator, but for the convection term, that will goes down, right? So when you're increasing the thickness, these two thermal resistance will move in the opposite direction. So if you draw it in terms of thermal resistance versus the R, and you have R1 to start with. For the conduction part, when you're increasing R2, the resistance will goes up, conduction, and for the convection, it will goes down. Right, but you are not dealing with individual components. You're dealing with the sum of these two. So when you add them together, you will end up with something like this. So that's your R total. And in fact, you will have a local, or you have a not local. In this case, there is only one extreme value, and that extreme value is your minimum total resistance. So there is a should say optimal R total because of these two competing factors, and that one is a minimum value. A minimum value means, I should say, at that minimum value, that radius called critical radius. So that one saying that if you want to apply certain insulation to your electric wire or to your steam pipe, you need to bear in mind what is this critical radius. So if the R2 is smaller than critical radius, right? If R2 is smaller than critical radius, when you're increasing R2, the total resistance actually is going down. So in other words, if R2 is smaller than the critical radius, the thicker insulation you put it on, the more heat you could lose, because the thermal resistance is going down if the radius is smaller than the critical radius. All right. So only when the radius is larger than the critical radius, when you're increasing R2, your resistance will going up, which means the thicker insulation layer will indeed insulate better. If it's below than the critical radius, the thicker insulation layer actually will insulate worse. All right, so that's what we learned from here. All right, that's it for today. That's the gen. That's for the generation. So we don't have any heat generated within the
Oh, okay.
We have some heat generated inside, but not across the thickness of our.
And this delta E delta E, that's the transient time.
So any that accumulated inside?
Yeah. Partial temperature versus time.
Yep. Okay, thank you.
That's just a quick question for the assignment. This is my first assignment here at Uni Melbourne.